Hello friends, till now during our discussion on operational amplifiers, we have talked about the basic op-amp modes, its parameters and the effect of negative feedback. And now we will move forward and start talking about bias current and offset voltage in operational amplifiers. Certain deviations from the ideal op-amp must be recognized because of their effects on its operation. Transistors within the op-amp must be biased so that they have the correct values of base and collector currents and collector to emitter voltages. The ideal op-amp has no input current at its terminals, but in fact the practical op-amp has small input bias currents, typically in the nanoampere range. Also, small internal imbalances in the transistors effectively produce a small offset voltage between the inputs. So, we are going to study the effect of these two on operational amplifiers. Effect of input bias current. Figure here shows an inverting amplifier with 0 input voltage. Ideally, the current through Ri is 0 because the input voltage is 0 and the voltage at the inverting terminal is also 0. The small input bias current I1 is through Rf from the output terminal. I1 creates a voltage drop across Rf as indicated. The positive side of Rf is the output terminal and therefore the output error voltage is I1 into Rf when it should be 0. Figure here shows a voltage follower with 0 input voltage and the source resistance Rs. In this case, an input bias current I1 produces a drop across Rs and creates an output voltage error as shown. The voltage at the inverting input terminal decreases to minus I1 into Rf because the negative feedback tends to maintain a differential voltage of 0 as indicated. Since the inverting terminal is connected directly to the output terminal, the output error voltage is minus I1 into Rs. The circuit shown in the figure is a non-inverting amplifier with 0 input voltage. Ideally, the voltage at the inverting terminal is also 0 as indicated. The input bias current I1 produces a voltage drop across Rf and thus creates an output error voltage of I1 into Rf just as with the inverting amplifier. Bias current compensation. As shown in figure, the output error voltage due to bias currents in a voltage follower can be sufficiently reduced by adding a resistor Rf equal to the source resistance Rs in the feedback path. The voltage drop created by I1 across the added resistor subtracts from the minus I2 Rs output error voltage. If I1 is equal to I2, then the output voltage is 0. Usually, I1 does not quite equal I2, but even in this case, the output error voltage is reduced as follows because IOS is less than I2. Therefore, V out error is equal to I1 minus I2 into Rs and is equal to IOS into Rs, where IOS is the input offset current. Non-inverting and inverting amplifiers. To compensate for the effect of bias current in the non-inverting amplifier, a resistor Rc is added as shown in figure. The compensating resistor value equals the parallel combination of Ri and Rf. The input current creates a voltage drop across RC that offsets the voltage across the combination of RI and RF, thus sufficiently reducing the output error voltage. The inverting amplifier is similarly compensated as shown in this figure. Effect of input offset voltage. The output voltage of an op amp should be 0 when the differential input is 0. However, there is always a small output error voltage present whose value typically ranges from microvolts to millivolts. This is due to unavoidable imbalances within the internal op amp transistors aside from the bias currents previously discussed. In a negative feedback configuration, the input offset voltage VIO can be visualized as an equivalent small DC voltage source as illustrated in this figure for a voltage follower. Generally, the output error voltage due to the input offset voltage is given by this equation where Vout error is equal to ACL into VIO. For the case of the voltage follower, ACL is equal to 1, so Vout error is equal to VIO. Input offset voltage compensation. Most integrated circuit op amps provide a means of compensation for offset voltage. This is usually done by connecting an external potentiometer to designated pins on the IC package as illustrated in figure for a 741 op amp. The two terminals are labeled offset null. With no input, the potentiometer is simply adjusted until the output voltage reads 0. Open loop frequency and phase responses. Open loop responses relate to an op amp with no external feedback. The frequency response indicates how the voltage gain changes with the frequency, and the phase response indicates how the phase shift between the input and the output signal changes with frequency. The open loop gain, like the beta of a transistor, varies greatly from one device to the next of the same type and cannot be dependent upon to have a constant value. Figure here illustrates the open loop and closed loop amplifier configurations. As shown in part A, the open loop voltage gain AOL of an op amp is the internal voltage gain of the device and represents the ratio of output voltage to input voltage. Notice that there are no external components, so the open loop voltage gain is set entirely by the internal design. In the closed loop op amp configuration shown in part B, the closed loop voltage gain ACL is the voltage gain of an op amp with external feedback. The closed loop voltage gain is determined by the external component values for an inverting amplifier configuration and is always less than the open loop gain. The closed loop voltage gain can be precisely controlled by external component values. Bandwidth limitations. In the previous sections, all of the voltage gain expressions were based on the mid-range gain and were considered independent of the frequency. The mid-range open loop gain of an op amp extends from 0 frequency up to a critical frequency at which the gain is 3 dB less than the mid-range value. Op amps are DC amplifiers as we do not have capacitive couplings between stages and therefore there is no lower critical frequency. This means that the mid-range gain extends down to 0 frequency and DC voltages are amplified the same as mid-range signal frequencies. An open loop response curve for a certain op-amp is shown in figure here. Most op-amp datasheets show this type of curve to specify the mid-range open loop gain. Notice that the curve rolls off at minus 20 dB per decade. The mid-range gain is 200,000, which is 106 dB, and the critical or cutoff frequency is approximately 10 Hz. Gain versus frequency analysis. The RC lag or low pass circuits within an op-amp are responsible for the roll off in gain as the frequency increases. From basic AC circuit theory, the attenuation of an RC low pass circuit, such as shown in figure, is expressed as V out over V in is equal to Xc divided by under root of R square plus X square C. Dividing both the numerator and the denominator to the right of the equal sign by Xc, we get V out over V in is equal to 1 upon under root 1 plus R square over X square C. The critical frequency of an RC circuit is given by this equation, where Fc is equal to 1 upon 2 pi RC. Dividing both sides by F gives Fc over F is equal to 1 over 2 pi RC and is equal to 1 over 2 pi Fc into R. Since Xc is equal to 1 by 2 pi Fc, the above expression can be written as Fc over F is equal to Xc over R. Substituting this result in the previous equation for V out over V in produces the following expression for the attenuation of an RC lag circuit in terms of frequency, and is given by this equation, where V out over V in is equal to 1 upon under root 1 plus F square divided by F square C. If an op-amp is represented by a voltage gain element with a gain of AOL mid plus a single RC lag circuit as shown in figure, it is known as a compensated op-amp. The total open loop gain of the op-amp is the product of the mid-range open loop gain AOL mid and the attenuation of the RC circuit, where AOL is equal to AOL mid divided by under root 1 plus F square divided by F square C. This equation shows that the open loop gain equals the mid-range gain when the signal frequency F is much less than the critical frequency Fc and drops off as the frequency increases. Since Fc is the part of the open loop response of an op-amp, we will refer to it as FCOL. Phase shift. As you learnt earlier, an RC circuit causes a propagation delay from input to output, thus creating a phase shift between the input signal and the output signal. An RC lag circuit, such as found in an op-amp stage, causes the output signal voltage to lag the input as shown in figure here. From basic AC circuit theory, the phase shift theta is given by this equation, where theta is equal to minus tan inverse R over Xc. Since R over Xc is equal to F over Fc, theta becomes equal to minus tan inverse F over Fc. The negative sign indicates that the output lags the input. This equation shows that the phase shift increases with frequency and approaches minus 90 degree as f becomes much greater than fc. Overall frequency response. Previously, an op-amp was defined to have a constant roll-off of minus 20 dB per decade above its critical frequency. For most op-amps, this is the case. For some, however, the situation is more complex. The more complex IC operational amplifier may consist of two or more cascaded amplifier stages. The gain of each stage is frequency dependent and rolls off at minus 20 dB per decade above its critical frequency. Therefore, the total response of an op-amp is a composite of the individual responses of the internal stages. As an example, a 3-stage op-amp is represented in figure A and the frequency response of each stage is shown in figure B. As you know, dB gains are added so that the total op-amp frequency response is as shown in figure C. Since the roll-off rates are additive, the total roll-off rate increases by minus 20 dB per decade as each critical frequency is reached. Overall phase response. In a multi-stage amplifier, each stage contributes to the total phase lag. As you have seen, each RC lag circuit can produce up to a minus 90 degree phase shift. Since each stage in an op-amp includes an RC lag circuit, a 3-stage op-amp, for example, can have a maximum phase lag of minus 270 degrees. Also, the phase lag of each stage is less than minus 45 degrees when the frequency is below the critical frequency, equal to minus 45 degrees at the critical frequency and greater than minus 45 degrees when the frequency is above the critical frequency. The phase lags of the stages of an op-amp are added to produce a total phase lag according to the following formula for 3 stages. Theta total is equal to minus tan inverse f over fc1 minus tan inverse f over fc2 minus tan inverse f over fc3. Closed loop frequency response. Op-amps are normally used in a closed loop configuration with negative feedback in order to achieve precise control of the gain and bandwidth. In this section, you will see how feedback affects the gain and frequency response of an op-amp. Here we shall first recall that mid-range gain of an op-amp is reduced by negative feedback as indicated by the following closed loop gain expressions for 3 amplifier configurations previously covered, where B is the feedback attenuation. For a non-inverting amplifier, ACL Ni is equal to AOL over 1 plus AOL B and is approximately equal to 1 by B and is equal to 1 plus RF over Ri. For an inverting amplifier, ACL I is equal to minus RF over Ri. For a voltage follower, ACL Vf is equal to 1. Effect of negative feedback on bandwidth. You know how negative feedback affects the gain. Now you will learn how it affects the amplifier's bandwidth. The closed loop critical frequency of an op-amp is given by this equation where FCCL is equal to FCOL into 1 plus BAOL mid. This expression shows that the closed loop critical frequency is higher than the open loop critical frequency by the factor 1 plus BAOL mid. Since FCCL equals the bandwidth for the closed loop amplifier, the closed loop bandwidth is also increased by the same factor. Figure here graphically illustrates the concept of closed loop response. When the open loop gain of an op amp is reduced by negative feedback, the bandwidth is increased. The closed loop gain is independent of the open loop gain up to the point of intersection of the two gain curves. The point of intersection is the critical frequency FCCL for the closed loop response. Notice that the closed loop gain has the same roll off rate as the open loop gain beyond the closed loop critical frequency. Gain bandwidth product. An increase in closed loop gain causes a decrease in the bandwidth and vice versa, such that the product of gain and bandwidth is a constant. This is true as long as the roll off rate is fixed, as in the case of a compensated op amp. If you let ACL represent the gain of any of the closed loop configurations and FCCL represent the closed loop critical frequency same as the bandwidth, then ACL FCCL is equal to AOL FCOL. The gain bandwidth product is always equal to the frequency at which the op amp's open loop gain is unity or 0 dB and is given by this equation where Ft is equal to ACL FCCL. So, here we come to the end of this lecture and therefore, we sum up. In this lecture, we learned that all practical op amps have small input bias currents and input offset voltages that produce small output error voltages. The input bias current effect can be compensated for with external resistors. The closed loop voltage gain is always less than the open loop voltage gain. The mid-range gain of an op amp extends down to DC. The gain of an op amp decreases as frequency increases above the critical frequency. The bandwidth of an op amp equals the upper critical frequency. Negative feedback lowers the gain and increases the bandwidth. The product of gain and bandwidth is constant for a given op amp. So, friends, this is it for today. See you in the next lecture. Thank you very much.